Welcome back to this final part of our two-part series where we're looking at meshless methods and how they apply to simulating nozzle dynamics. For those of you who skipped the first video, let me reintroduce myself. My name is Joubert from the University of Pretoria, and in this video we're going to be looking at some of the results that I put together with my collaborators, Professor Nico Wilke, also from the University of Pretoria, and Patrick Pizette from IMT North Europe. And in this video, we're specifically going to be focusing on converting the information from our particle systems to something that we can process and understand, essentially extract information from. As with the first video, I'm going to just start off by giving a very brief overview of what we're going to be looking at. First of all, let me mention that the modeling and simulation aspects of this are covered in part 1. So for those of you that are interested in what meshless methods are, how we solve the pressure-Poisson equation, and how we handle the multiphysics extensions, I would direct you to go look at the first video. When we're specifically focusing on what we're going to be dealing with in this video, we're going to be essentially describing a way of turning the results from our particle system into something that we can use to really understand a specific process. In this case, we're going to be focusing on atomization. So for that, I'm going to be discussing our post-processing and analysis pipeline, really focusing on how we extract information from images that we are generating from particle data. We're going to move on to the problem setup by looking at the geometry and boundary conditions of the nozzle that we're looking at. And then when we look at the results, first I'm going to present a base case simulation and the results that we get from the base case. And then finally we follow this up with a geometric study that looks at how we can use this post-processing pipeline to carry out a geometric study, or to understand how the geometry of a nozzle influences our results. So why is it even interesting to talk about post-processing and analysis for meshless Lagrangian methods? We have the data, surely all the information that we could want is in there. Well, if we're looking at the case of atomization specifically, as we are in this video, we want to know what type of nozzle geometry works best to promote atomization. However, from the simulation that we get back, all that we recover is point cloud information that's assigned to each individual particle, and these come from low fidelity simulations. This means that we don't have particles that are small enough to really resolve individual droplets. So how do we estimate droplet sizes if we can't actually resolve droplets? Well, the short answer is we can't. So we need to use some other proxy that can predict which types of nozzles promote atomization. For this, we assume that droplet formation directly correlates to interface area. This of course means that we need to find a way to resolve these interfaces to begin with. Said differently, we need to be able to distinguish one phase from the next. There's a few different fields we can use to determine this type of information, with the two natural choices being the density or the color gradient as described in the previous video. With the density field, we can immediately see which particles belong to which fluid phase by simply looking at the density. Since we are dealing with incompressible flow, the density does remain unchanged, so this gives us a binary distinction between which phase a particle actually belongs to. An alternative approach is to use the continuum representation of this interface by looking at the color gradient. Specifically, what you see here is the color gradient magnitude. Rather than being able to distinguish between different phases, as with the density, the color gradient is very sharp in regions where there's an interface between the two phases. This means that we lose information about which material is in which phase, but we do build up the measure that we are interested in, specifically some measure of surface area itself. To reiterate the points on the previous slide, here we can see a simulation at the outlet condition of our nozzle with the fluids mixing. Again, we're comparing the density to the color gradient magnitude. From this, it becomes very clear why we would prefer the color gradient over the density field. Even though we might be able to extract surface areas, the real reason why we prefer the color gradient is because it gives us information about really the subgrid surfaces as well. Specifically, when you look at the regions of high color gradients, that essentially maps directly to the interface that we will be able to extract directly from the density results. Also, similarly, where we have zero gradients, This is similar to the place where we've got a single phase in that region. Of course, here the density is more informative because it tells us some information about which phase is in that region, but really the area where the color gradient completely outshines the density field is in regions where there is some mixing taking place. Specifically, we don't just get this region that tells us here is an interface. We get a region that tells us here is a mixture of different particles that depends on the overall magnitude of the color gradient. So now that we've chosen the magnitude of color gradient as our scalar field that we will be using to construct these images with, we can have a look at our actual post-processing pipeline. So of course we start by taking in the data from our particle simulation. Like I mentioned, we're taking in only scalar data here, of course the color gradient magnitude in this case. We then take a grid overlaid over the scalar data and simply convert this into a black and white image, where of course the magnitude of the color gradient directly maps to the color in our image. We do this for several time steps over the course of the simulation. In this case, we do it for 400 images, and we average those 400 images. Once we have this average image, we send it through a 2D FFT, and of course, in order to make this FFT data a bit more interpretable, we do again another 1D projection, and then we can use these projected data to estimate length scales of the information in the system. So with that in place, we can now look at the actual problem that we're trying to simulate. So the geometry of the nozzle that we're interested in is this long tube that has a heavy fluid flowing through the main column. This long tube has 3 sections, a part where it contracts, a part where we put gas injection, and an expanding section. As you can see here, we've got 6 tubes feeding the high pressure steam into the main cavity. And then finally, you can see on the outlet of this nozzle, we also put down our image mesh. This is where we generate the image that we use for our FFT. Our baseline case uses a geometry made up of only cylindrical tubes. Since this means that we have cylindrical symmetry, at least in the outlet geometry itself, we can use a slightly simpler approach to post-processing. Rather than do a 2D FFT, we take a 1D slice of the outlet where we start from the origin and move radially outwards, and then perform 1D FFTs on this one-dimensional slice. This, of course, gives us one additional degree of freedom in the form of the line's orientation. For this, we sweep our line angles over the full revolution in 64 equal increments. We then, of course, do this for each of the 400 images. The spectral results show the expected exponential decay in information over length scales until we reach the particle size. Then we can see that the information remains roughly constant. We can also see some spikes in the spectral data. As it turns out, these spikes are associated with the length scale of the primary and secondary fluid columns that you see in the outlet image. Since we're now comparing designs that do not necessarily have cylindrical symmetry in the geometry, we have to utilize the 2D FFT slices to compare everything fairly. For this, we performed the full post-processing analysis on the cylindrical case as well. Here you can see the 2D FFT results for both the current design and the proposed update. You can of course see a qualitative difference between the 2D results already, specifically seeing the influence of eccentricity in the nozzle outlet. To really recover the quantifiable measure, however, we need to look at the 1D projection. In order to generate this projection, we combine the feature length scales in the x and y direction and recover an effective length scale. First of all, from a qualitative perspective again, we can see similar trend between the 1D results. Specifically, we can see that the cylindrical case has a very similar structure to the new proposed design. However, it does contain a lot more structure in its FFT data. This does indicate that the proposed design also induces more mixing. Quantifiably, we observe approximately 20% increase in the low frequency information, followed by 15% increase in high frequency information, up to the particle length scaling. And so in conclusion, we utilized the multiphase incompressible GFD method that we discussed in video 1 to simulate gas injected into a liquid stream in a nozzle environment. We saw that the color gradient provides an insightful measure into the mixing behavior, and we saw how a 2D FFT can be used to produce a qualitative comparison between mixing behavior of nozzle designs. Of course, what I haven't discussed here is experimental validation, as well as comparing our FFT results to other versions of information measures, such as informational entropy. And of course, it would also be useful to compare these techniques to other mixing measures as well. And with that, I'd like to conclude this 2-part series. Thank you so much, especially for all of those who stuck with me for both the videos. If you have any questions or comments for this video or the previous video, please feel free to let me know in the comments below, or you can contact me at the email provided on screen. I'm going to again provide the same references that I provided in the first video for anyone that's interested in to explore this work in a little bit more detail. We go into both the modeling as well as really understanding what the FFT information tells us about these simulations in a lot more detail in the papers provided below. Thanks so much for dropping by. See you around.